Okay, so we'll continue our discussion on spatial coherence. So more specifically, last time we looked at the angular spectrum representation of fields. So we'll just confine ourselves to fields propagating in the positive z direction. Because the physics doesn't change for the negative z direction. So just to recapitulate what we did last time. So any field u of rho z, which is nothing but rho is xy. Can be written this way in terms of the spatial frequency variables qx and qy. So just to recall, rho vector is xy, q vector is qx, qy. So this is our k vector. And this is our q vector. Qx, qy. And kz is denoted by the letter w. Right. And so k cannot be written as. So these are qx and qy are basically the wave vectors, the spatial wave vectors, the plane perpendicular to the direction of propagation. So we saw that u of rho z satisfies the Helmholtz equation. So, and then we saw that the so this is the differential equation for u tilde. And of course, w has two parts. One is the propagating wave solution if w is positive, because please note that w square is k square minus qx square minus qy square. When you take the square root, it could be either positive or negative. So the positive root corresponds to the propagating field. Propagating field solution. And the imaginary part corresponds to the evanescent field. So this is the so this one is if of course we won't be concerned we won't bother ourselves with the evanescent field solution, but that doesn't mean that it's not important. So evanescent fields play a very important role in near field optics, but we won't be getting into near field optics in this course. So we'll only concern ourselves with the propagating field solution. So of course the general solution for U tilde is so we will, if you just consider the field traveling in the positive z direction, so we are only interested in the field traveling in the positive z direction. So we will ignore B. So which means U of x, y, z
Excuse me. Sorry to disturb.
Yeah.
Subscripts are not so clear. Can you just make it a little bigger?
Yes. So which all the subscripts?
From now till now, it is understandable. I'm just informing.
Sure. Sorry about it. So
thank you.
So now are the subscripts clear?
Now it's okay.
Okay. Thank you.
Yeah. Thank you.
Please note that this is not a Fourier relationship in general, because you have x, y, z, and we are only integrating over qx and qi. So however,
can you see the board? Yeah.
Can you see the board?
It became a little dark, but yeah, we could see.
Okay.
Okay, now you should be able to see the board clearly, right? It should be.
Yeah. Now it's clear.
Okay. So at z equals 0, we have likewise. Now this is a Fourier transform. So at z equals 0, u of xy is the Fourier transform of a of qx qy. So likewise, we can invert this relationship. So please note that u and a form a Fourier transform pair only when z is 0, only when you set the source plane to be at z equals 0. In general, u and a do not form a Fourier transform pair. Now, a of qx qy, this quantity is called the angular spectrum representation of the field. Propagating in the positive z direction. So which means once we know what a of qx qy is, we should be able to calculate the field at any z. Okay, so that's the advantage of the angular spectrum representation. So once you please note that a of qx qy doesn't depend on on z. So once we know what the angular spectrum of the field is, we pretty much know what u is. Okay, so we pretty much we can express u at any x, y, and z, right? So that's the advantage of the angular spectrum representation. So now let us take this analysis forward.
So here, if you look at this expression for u, x, y, z.
Oh yeah, I can write it on one side.
You don't have, I mean, basically, don't take z is equal to 0, arbitrary z.
Yeah.
So now, if you look at there, so I take these e to the power wz,
right,
on the left hand side, e to the power minus wz. That I can do because I have no integration over.
True.
So then the function on the left hand side will become u of xyz times e to the power minus iwz.
That is true.
Okay, and whatever you have on the right hand side, you can think of it as a Fourier transform of that function, right? That e to the power I mean, u times u of x, y, z
Yes, yes, yes.
multiplied by e to the power minus w I w z, I to w z.
That is true, except that the right hand side, when you have x and y dependence, qx, and you're integrating over qx and qy.
That is true.
Yeah.
Now what you do, because this right hand side you can think of now is a Fourier transform of some function of x and y.
That is true. Yes, yes. The right hand side is basically a Fourier transform.
So now if you apply the inverse Fourier transform,
Uh-huh.
It will be there. This e to the power minus I w z will be there, right?
Um,
Because that then you just do this. So this basically what it tells you is that if I look at this quantity,
yes.
it doesn't matter what value of z you take.
So here,
Yeah, I mean, if you take u of x, y, z
yes,
times e to the power minus I w iota minus
yes, yes, yes.
e to the power minus I, yes, you take u of x, y, z times e to the power minus I w z.
That is
This will
correct.
be equal to this quantity.
Yes, this will be equal to the integral. Yes,
Right.
yes.
So now you can do the inverse Fourier transform of this.
Yes. So, or
Because on the right hand side there is no z dependence.
that is true. Right hand side there is no z dependence. It only comes in the exponent.
Yes.
Yes. So there is no. It
No.
doesn't come in the argument of.
Yes. So therefore, I can, in principle, take the inverse Fourier transform
Uh,
on both sides.
y-
So therefore, what you are writing here for z is equal to 0.
So yes, so in a sense, yes, but typically, of course, when we do this transformation, we always go from a
When you measure, of course, you'll have to fix some value of z.
Yeah.
I agree. But no, it doesn't matter what value of z you take, whether you take z is equal to 0 or something else. Because that anyway it is not going to affect.
that is true. It's because because the angular spectrum does not have any z dependence. It doesn't. That is no, in a sense that is true. No, that is true. That is true. No, you're right, because it doesn't matter, because all you can do is probably, yes, in a sense, all we have to do is just have the angular spectrum, integrate it out over qx and qy, and multiply it by e power I wz on the right hand side, and that will pretty much give us the field at arbitrary z.
It doesn't matter whether you take z is equal to 0 or anything else.
That is true, yes. So this was done only to show that, of course, when z is 0, this goes away. So formally speaking, you have xy and qx, qy. The
point is,
yeah.
that is true, but
Yeah.
it doesn't matter what value of z.
That is true. Yes, yes, yes. You're right. Essentially, that's what we are doing. So, yeah, that can be done, because even if,
So in other words, on the wave propagation direction, if you take your image plane or wherever you put your observation, your detector, it doesn't matter where you put, right?
that is true. That is true. So it doesn't have to be at z equals 0. For convenience, we just fix it at z equals 0, so that it doesn't.
This translational symmetry is there.
That is true. Yes, absolutely. So the only thing is, if we don't put the source plane at z equals 0, it will just show up as a phase factor in somewhere in the analysis. But that's not going to change the physics or.
Here it doesn't matter where you put.
That is true. That is true. That is, yes. That is true. So one more thing is, of course, the angular spectrum in the lab. That is something that we determine from the source. In a sense, from the properties of the source, we can model the angular spectrum. So typically, the angular spectrum will have a Gaussian form, because that's the model we pretty much use. So that's the famous Gaussian shell model source, where we model the angular spectrum of the source to be to have a Gaussian form. So once again,
so okay, just
yeah.
So if I take these, these thermal light, so there also the angular spectrum should be a Gaussian form?
So typically for yeah, so these are incoherent sources. So you could model them to be a Gaussian. Even though for a laser, certainly we model the angular spectrum to be a Gaussian.
Yeah, this is a completely incoherent source. So there.
But I have not seen the explicit form of the angular spectrum for an incoherent source. No, it can be done. Of course, one can always because you can also always let an incoherent source propagate and it can become coherent. That is the famous Van Ziterke Zernike theorem, Van Ziterke-Zernike theorem. But I don't know on top of my head whether an incoherent source, the angular spectrum of an incoherent source, is always taken to be a Gaussian.
A laser source, of course, you can.
It's a Gauss. So we just so what we do is we just so substitute for A here. So when we do this, we get so using different variables, dummy variables. So this is what we have. So once again, so that's what we have here. So now we so now so one, of course, once we know this one can formally carry out this integration. But now we make an approximation called the paraxial approximation. So let us assume that much less than k squared. So in this case, and it can be written as because q square, qx square plus qy square is q square. So this is called paraxial approximation. So what does it tell us? What is the physical meaning of this approximation? It just tells us that the field is propagating mostly along the z direction. The spread in the transverse plane is much smaller. It's negligible. So in other words, we are dealing with a beam-like solution propagating along the z direction, and it's not spreading too much. Or when I say not spreading too much, the effect of diffraction is not that much. Okay. So in other words, we're dealing with a beam-like solution, and under paraxial approximation, the effects of diffraction are negligible. So so let us recall this one. We have seen this expression many times. So we are just going to rewrite this once again under paraxial approximation. So q dot rho is basically qxx plus qiyy. And this d square q is basically dqx dqy. So under paraxial approximation, so this comes out. So this is what it is. So yeah, the point that you made earlier, Professor Ghosh, so probably, yeah, so if we don't want to work in terms of the field at z equals 0, probably once we know the angular spectrum, if we know that we are going to enforce the paraxial approximation, just we can multiply by this factor and integrate it out over q, and then insert this phase factor by hand once this is done. So this will then give us the field at arbitrary z.
No, see, thing is here, of course, things will be.
Oh no, here of course the z comes here explicitly. Here the z comes here.
But earlier it was
Yes. So here, of course, I'm sorry. Now I take back my words. So here Z, the dependence comes here explicitly.
Yeah, under paraxial approximation, I think it will matter where you put your.
Yes. So under paraxial approximation, that is true. So probably that's why for convenience we put the source at Z equals 0. Because since we know the source, we know what the field is at the source. So then, of course, as it propagates, the field will change its and so yeah.
No, if you take the paraxial approximation, then this translational symmetry along the propagation direction is no more there.
That is true. Yes, that is true.
Because Z going to Z plus Z naught, it will change things.
That is true. Yes, that is true. Because in that case, yeah.
Replace Z by Z plus Z naught. So then the expression on the right hand side will change.
That is true. Yes.
That translational symmetry is no more there.
Yes. So then under paraxial approximation, we will have to fix the source somewhere and then determine the field at the source. Then we know the angular spectrum.
Therefore, under paraxial approximation, these, the field loses its translational symmetry.
Yes.
Along the propagation direction. Yeah, although it is small effect, but still, because this q square by k is small.
Its q square by k is negligible, but formally, since it carries a z dependence, we cannot just throw it away. So this is between the paraxial effect. So once we know this one, we should be able to calculate the correlation function. So we just start with this definition. So which means, not the definition, I mean, we start with this expression for u of rho z. So this is a four-dimensional integral. So dq1x, dq1y, dq2x, dq2y. So this is the correlation function between the field vibrations at rho 1 and rho 2. So this quantity, that's the quantity that we have written down here. This is symbolically denoted, and this is called the cross-spectral density function, similar to what we saw in that temporal coherence case. And this one called the angular correlation function. Of course, when we say angular, it doesn't mean that any theta or phi an angle variable is involved. It just means the correlation of the angular spectrum. So it's called the angular correlation function. So once again, can be written as capital A Q2. This capital A of Q1, Q2 is basically this one. So just that's what it is. So once again, oh, did I? Oh, yeah, sorry. Yes. So once again, the source is placed at z equals 0. Just becomes so. Now we have so basically we are trying to write down the spatial analog of the generalized Wiener-Khinchin theorem. So yeah, so A of Q1, Q2 So this is so that's what it is. This is the spatial analog of the generalized Wiener-Khinchin theorem. So once again, we can define the degree of coherence. So this W of rho 1 is nothing but S of rho 1. It's just a spectral density. And as always, the degree of coherence always takes a value between 0 and 1. If it is 0, the field is incoherent, and if it is 1, the coherence is maximum. Now, for a spatially stationary random process, is W of delta rho. Because the process is stationary, then the cross-spectral density depends only on the difference in the spatial coordinates, very similar to analogous to what we saw in the temporal case, where over there the cross-spectral density only depended on the time difference tau, T2 minus T1. Likewise here, the cross-spectral density will depend on delta rho, not the absolute values of rho 2 and rho 1. So which means A of, so this is what it is. So this is how the angular spectrum, the correlation, the angular correlation would be for a spatially stationary random process. And so this is the spatial Wiener-Khinchin theorem. Okay, so now we'll try to write down the intensity. So how do we express the intensity that we measure at the detector in terms of the cross-spectral density functions and the degree of coherence. So basically what we are going to do is we're once again going to consider Young's double slit setup, Young's double slit interferometer.
Maybe one what can ask is that if we don't do this paraxial approximation, so can't we, follow this procedure of
this procedure? Of course, this procedure will hold good independent of paraxial approximation.
So what advantage does it give by going through this paraxial approximation?
So one thing is, under paraxial approximation, you can ignore the spreading of the beam. So the diffraction effects can be ignored, neglected. So that's one thing. And also you can always assume that the propagation is highly directional.
Yeah, no, that is true. That all.
That's the other.
In terms of effects, like if I want to study the coherence, spatial coherence or temporal coherence, does it help?
So if one so if you don't make the paraxial approximation, so the paraxial approximation certainly doesn't influence the coherence of the source.
Yes, that is not.
But the only thing is, if we are going to study the propagation of coherence, then of course the answer would depend on whether or not we enforce the paraxial approximation. So, but if the goal is only to see how the source is correlated at the source plane, then I don't think you really the paraxial approximation gives any advantage.
Yeah, but, I can. So the question is that if the source has some amount of coherence, right?
Yeah.
Maybe temporal coherence or spatial coherence. And now I allow this paraxial approximation. So under certain condition, the field is basically behaving like a paraxial. So then there will be some modification in the coherence, right? Or not?
So there will be a modification in the coherence. Yes, when we try to measure the coherence at some finite z away from the source plane, because then in a sense we have allowed the coherence to propagate from the source plane. So then there will be some difference because of the approximation that we have made. But physically, I don't know how significant that difference will be. In a sense, the only physical consequence of enforcing the paraxial approximation is we ignore the diffraction effects.
Yeah, that is good. That is good. You ignore the diffraction effect, but I mean, you ignore the diffraction effect, but apart from that, does it help? I understand that this is much relatively easier to handle with the field propagation and all.
That is true. So the analysis is relatively simpler under paraxial approximation.
In lab, only deal with the paraxial.
That is true. Because we make the beam, so we try to ignore the spreading of the beam in the lab. It's more a collimated beam.
More a collimated beam, yes. Otherwise, most of the experiments, you cannot do.
Yes, it's hard to make measurements. So in the lab, naturally, the paraxial approximation is enforced. But beyond that, I don't know whether, I don't think.
But what happens to the free propagation of paraxial wave, So I have this field, but then it is not just stationary, right? It will also propagate.
That is true. That is true.
So will it change this beam waste or something like
Oh, yes. So eventually, yes. So the waste, even under paraxial approximation, it cannot, in real world, it cannot be enforced forever. We can't just let the beam propagate for an arbitrary distance and still, and assume that we are operating within the paraxial approximation. The waste of the beam will change with distance, with time as it propagates. So what we are trying to do is, when we do experiments or when we do any analysis, we try to confine ourselves to the situation where the waste of the beam doesn't change.
Yes.
And the diffraction effects don't kick in, or there is diffraction, but where we can safely assume that the effects of diffraction are negligible.
Right.
So the beam is collimated. So we always work in that regime.
Yeah, otherwise, even if you take paraxial approximation, it will, the beam waste will change, like with respect to time.
That is true. That is true. It will change. It will change with distance and time. So the beam waste is always expressed as a function of z, even in paraxial approximation.
Right. So therefore, you'll have to take some z or some range of z where it is not changing much.
That is true. And we take the beam waste as a function of z because we have enforced the paraxial approximation. So even under the paraxial approximation, the waste will change with z. But if we don't enforce the paraxial approximation, then I don't think the beam waste will only depend on z. Then the transfer spatial variables will also, it will depend only also on the transfer spatial variables.
And those things are much more difficult to handle.
Exactly. That problem becomes much harder. So then the question is, when we have to take into account how it spreads in the transverse plane.
Yes. Right.
But one thing is, the beam waste will change even under paraxial approximation with distance, with z.
But that change is, is not arbitrary change.
It's not abrupt. So we for a Gaussian beam, this can be worked out. We have a formula that tells how the beam waste will change with z. So the question is, do we want to beam waste to change, or do we just restrict ourselves in?
No, whenever you do these optics with paraxial light, paraxial optics, so one will have to have this thing in mind that how much amount we can allow the beam propagation.
That is true.
Because within that you'll have to do the experiment. Otherwise, it's okay.
That is true. That is true. That is true. That is true. That is true.
But till even if you don't take paraxial optics, still one can do it.
No, one can do. It's just that the analysis will become much more involved. But it can be done. So all these properties, coherence, they independent of the paraxial regime.
Exactly.
So paraxial approximation is only to simplify the problem, and it's a good approximation for a wide variety of problems in the lab.
Yeah, most of the optics experiments are done with paraxial beams. Right?
Yes, with paraxial beams, yes. Okay, so now let's once again consider the Young's double slit setup. So this is one slit. So this is the point of point of observation. So this is so this is something that we have already seen. The total field at the point of observation is just the sum of the fields passing through the two slits. So this is what we have.
Sorry, can you just remind me what is this omega here?
Oh, so omega is just that frequency
Frequency
of the source, but that is just included for the sake of completeness. So when we discuss spatial coherence, we don't really have to worry about the frequency. So these two are the interference term. The CC stands for complex conjugate. The second term is the complex conjugate of this one. So this can be written as the first, the average here on the first term is basically the intensity of light passing through the first slit. So that can be written as S of rho 1. Likewise, the second term is the intensity of the field passing through the second slit. That can be written as S of rho 2. And the third term, this one, is the cross spectral density. Right, plus the complex conjugate. Now, K1 star K2 can be written as K1 K2 some e power I phi k, some phase factor, right? Likewise, W of rho 1 rho 2 can be written as Now this whole thing is nothing but mu of rho 1, rho 2, the complex degree of coherence. This complex degree of coherence can be written in terms of its modulus times phase factor. Okay. So now we put everything back into this expression here. So we get, so this is the intensity at the point of observation. So we would get, I can just write it as S of rho. This is the intensity this is nothing but so this is how we relate the intensity of the field measured at the point of observation to the degree of coherence, to the spatial degree of coherence. Now, there's another quantity, visibility, Imax minus Imin by Imax plus Imin. The visibility of the interference patterns. So that's what it is. So so the special, so for the special case, if so in this case, the visibility will simply depend only on the degree of coherence. So for perfect coherence, we get the maximum visibility 1, and for complete incoherence, there won't be any interference pattern. Visibility will be 0. Right. So now let us consider the case, the three cases, very similar to what we did in the case of temporal coherence. And then we'll wrap up our discussion on spatial coherence, and from Tuesday, from next week, we'll start quantum theory of coherence. Case 1. No correlation between different spatial frequency components. By spatial frequency, we mean Q. Qx and Qy are the spatial frequency component. So if there is no correlation between different frequency component, the angular correlation will be expressed by this delta function. So that tells us that there is no correlation between Q1 and Q2. So in this case, so the cross spectral density basically becomes the spectral density of the field. So the Q1 can be replaced by Q, and rho 2 minus rho 1 is delta rho. And again, this W depends only on delta rho. So this is the case of no correlation. The second extreme case is the case of perfect correlation. Frequency component. So that is the case where the angular correlation the ensemble average simply becomes equal to this perfect correlation, so there is no randomness in the system. Okay. So in this case, U of rho z so this is then in this case there is no ensemble average, and then you can, the angular spectrum is no longer symbolic. In general, when the coherence is partial, the notion of angular spectrum assumes a physical meaning only when we talk in terms of correlations. So in the case of perfect correlation, this you have an exact expression without any ensemble average. And the more realistic scenario is the case of partial correlation between different spatial frequency components. And we'll stop with this. So a model that really captures the partial correlations is the Gaussian shell model. So So this is the Gaussian shell model source. So in the limit delta t approaching 0, we get back case 1 because this becomes a delta function. The second Gaussian becomes a delta function. So that is a case of no correlation. So there is no whole square here. It's q1 square minus q2 square in the first term. In the other extreme case, when delta c approaches infinity, this becomes 1. So then we get case 2, which is perfect correlation because you can separate the first Gaussian. You can write it as a product. So whatever analysis we carried out in the case of temporal coherence, we can play the same game. We can carry out a similar analysis for the case of spatial coherence as well. Okay, so perfect correlation and then no correlation are the extreme cases. In all the problems that you investigate in the lab, case 3, partial correlation is what one would have. So typically we always use the Gaussian shell model. So this is one of the well-studied models to study spatial and temporal coherence. Okay. So with this, we wrap up our discussion on optical coherence in classical optics. So from next week on Tuesday, we will start our discussion on quantum theory of optical coherence. and then discuss some quantum states of light and go to interferometry, Hongo-Mandel effect, Hansberry-Brown twist experiments, so on and so forth. Okay. Any questions from the online participants?
No, sir.
Okay, then we'll meet this Tuesday at 2:50.
Yeah.
Thank you. Thank you.
Thank you.